Hi everyone, and welcome to our Introduction to Digital Forensics session. I'm Raymond Musumba, and I'm excited to take you through this fascinating field that's becoming increasingly important in our digital world. Today, we'll explore how digital evidence can help solve crimes and disputes, using examples particularly from Kenya and across Africa. Whether you're from law enforcement, corporate security, or just getting started in digital investigations, this session will give you a solid foundation to understand how digital forensics works in practice. By the end of this session, you'll have 4 key abilities. First, you'll be able to define digital forensics and understand the step-by-step process investigators follow. Think of it like being a detective, but instead of looking for fingerprints, we are looking for digital footprints. Second, you'll recognize different types of cybercrimes and know the proper procedures to handle digital evidence. This is crucial because one mistake can make evidence inadmissible in court. Third, you'll identify where digital evidence can be found and how it answers the fundamental questions every investigator asks. Who did it? What happened? When did it occur? Where did it take place? Why did it happen? And how was it done? Finally, you will understand the challenges investigators face and how to overcome them. In Kenya particularly, we've seen cases where poor evidence handling has led to cybercriminals walking free. So these skills are more important than ever. To briefly introduce myself, I'm a certified fraud examiner with over 8 years experience in forensics and information security, complemented by over 15 years experience in full stack development. I've worked on digital forensics cases across multiple industries, from banking fraud to mobile money scams. I've published research with organizations like Serianu, which some of you might know as one of East Africa's leading cybersecurity firms. My experience spans small business compromises to large-scale corporate investigations, so I'll be sharing real-world examples throughout the session. Let's start with the basics. What exactly is digital forensics? Think of it as the science of finding and analyzing digital clues. Digital forensics is essentially detective work for the digital age. It's a branch of forensic science that deals with finding, preserving, and analyzing evidence from electronic devices like computers, smartphones, and tablets. The key phrase here is supporting legal proceedings. This means our work must be done in a way that a court of law will accept it as valid evidence. Last year, for example, there was a case where an employee at a Nairobi bank was suspected of transferring money to unauthorized accounts. The digital forensics team had to examine his computer, phone, and email records to prove what happened. They found deleted emails, recovered WhatsApp messages, and traced the electronic money trail. But here's the crucial part. They had to do all this while following strict procedures, because if they made even one mistake, the evidence could be thrown out of court and the suspect could walk free. Digital forensics is different from regular computer repair or data recovery because everything we do must be legally defensible. We can't just fix a computer. We have to preserve it exactly as we found it, make copies, and document every single step we take. Digital forensics isn't just one thing. It's actually made up of several specialized areas. Computer forensics deals with laptops and desktop computers. This is often where we find business emails, financial records, and documents. Mobile forensics focuses on smartphones and tablets. And this is incredibly important in Kenya, where mobile money such as M-Pesa is widely used. Think about it. Your phone probably contains your M-Pesa transaction history, WhatsApp conversations, location data, and photos with timestamps. Network forensics, on the other hand, examines internet traffic. This is useful when investigating online fraud or unauthorized access. Email forensics specifically looks at electronic mail, which is often crucial in corporate investigations. Cloud forensics is growing rapidly as more businesses use services like Google Drive and Microsoft OneDrive. Memory forensics examines computer RAM, which can show what programs were running and what passwords were entered even if they were deleted. IoT forensics is becoming more relevant as smart devices become common in homes and offices. Vehicle forensics examines data from modern cars, which might seem unusual, But if you think about it, vehicles these days contain GPS data, communication logs, and operational information that could be crucial in investigations. Now that we understand what digital forensics is, let's look at where we actually use it in real life. Technology is advancing rapidly. We've gone from basic mobile phones to smartphones with internet banking in just a few years. Unfortunately, cybercrime is growing just as fast. Digital forensics helps us answer the 6 fundamental questions that every investigator needs to know. That's who, what, when, where, why, and how. Let me walk you through some common cybercrimes. Unauthorized access or hacking might involve someone breaking into a company's system to steal customer data or financial information. We've seen cases where hackers accessed banking systems and transferred millions of shillings to foreign accounts. Unauthorized interception includes things like man-in-the-middle attacks, where criminals intercept online banking sessions. Identity theft is a big one in Kenya, and criminals steal someone's ID number, phone number, or M-Pesa details to impersonate them. Phishing involves fake emails or SMS messages designed to steal login credentials. You've probably received fake messages claiming to be from your bank or mobile provider. Computer fraud covers everything from fake online shops to take your money but never deliver goods, to employees manipulating company financial systems. We also see cases of false information being published online to damage someone's reputation or manipulate stock prices. Each of these crimes leaves digital traces that forensics experts can follow. When we investigate these crimes, we can't just make it up as we go along. We follow internationally recognized standards and best practices, such as those from the Scientific Working Group on Digital Evidence and the National Institute of Science and Technology, better known as NIST. These standards ensure that investigations conducted in Kenya, for instance, meet the same quality standards as anywhere else in the world. This is crucial because cybercrime often crosses borders. A criminal in Nigeria might target a victim in Kenya using servers in South Africa, for example. This 5-phase process is generally one that every professional investigation follows. Let me walk you through each phase with a practical example. Imagine we're investigating a case where an employee at a Nairobi company is suspected of selling customer data to computers. In phase 1, we identify what digital evidence might exist. This could be the employee's computer, phone, email account, access logs to customer databases, or CCTV footage. We also obtain legal authorization. In Kenya, for instance, this might mean getting a warrant from a magistrate or written permission from the company if it's an internal investigation. In phase 2, we secure and isolate all evidence sources. The employee's computer gets unplugged and sealed. We document who was present, take photographs, and start our chain of custody documentation. This is like a detailed diary of who touched what evidence and when. In phase 3, we create verified forensic images using specialized equipment. Think of this as making a perfect digital photocopy of the entire computer hard drive, including deleted files. We use write blocking technology to ensure we don't accidentally change anything on the original evidence. In phase 4, we examine the forensic images to recover deleted files, analyze email communications, check internet browsing history, and reconstruct the timeline of events. We might find deleted emails to competitors, evidence of unauthorized database access, or attempts to cover up the crime. In phase 5, we document everything we found, prepare court-ready reports, and may provide expert testimony. The report must be clear enough for a judge or jury to understand, even if they are not technical experts. It's important to note that these phases often overlap, documentation happens throughout, and we maintain chain of custody and quality assurance at every step. This ensures our evidence will be admissible in court. Before we can investigate, we need to know where to look for digital evidence. Let's explore the various sources. The ability to identify potential sources of digital evidence is like knowing where to look for clues at a crime scene. In the digital world, evidence can be found in many places. Computers are obvious sources. They contain hard drives with files, RAM, Windows registry entries that track program usage, system logs, emails, and web browsing data. Even if someone deletes files, we can often recover them. Removable media includes USB drives, external hard drives, memory cards, and even old CDs or DVDs. Many people use USB drives to transfer files between computers, and these often contain copies of important documents. Mobile devices are gold mines of evidence. They contain call logs showing someone talked to, SMS messages, GPS data showing where someone has been, app data from applications like WhatsApp, Facebook, or mobile banking apps, and photos with timestamps and location information. In Kenya, for example, where mobile money is ubiquitous, M-Pesa transaction records on phones are often crucial evidence. IoT devices, on the other hand, are becoming more common. Security cameras, smart TVs, printers, gaming consoles, and even fitness trackers. These devices often store more data than people realize. For example, a smart TV might record what channels were watched and when, or a printer might store copies of documents that were printed. Cloud services like Google Drive, Microsoft OneDrive, Dropbox, or iCloud can contain synchronized files, emails, and backup data. Many people use these services on their phones and computers, often without realizing how much data is stored there. GPS systems in vehicles can show where someone traveled, when they were there, and what routes they took. This is particularly useful in cases involving delivery drivers, taxi operators, and company vehicles. Once we know where the evidence is, we need to preserve it properly. This is where many investigations succeed or fail. Here's something important to understand. Criminals don't want to get caught. They actively try to hide, destroy, or alter evidence. They might delete files, clear browser history, format hard drives, or even physically destroy devices. Our job as investigators is to work faster and smarter than the criminals. We need to preserve evidence before it can be destroyed or altered, whether that destruction is intentional by the criminal or accidental by well-meaning people who don't understand digital forensics. This is why speed and proper procedures are so critical in the first hours of an investigation. We preserve digital evidence to ensure three critical qualities: integrity, consistency, and admissibility. Integrity means the evidence hasn't been changed or corrupted. Consistency means we get the same results every time we examine it, and admissibility means a court of law will accept it as valid evidence. If we fail in any of these areas, our investigation becomes worthless from a legal standpoint. In Kenya's legal system, for instance, judges are becoming increasingly strict about digital evidence standards, so proper preservation is more important than ever. There are a number of methods used to preserve digital evidence. First, maintaining a chain of custody, which is a detailed record of everyone who has handled the evidence, when they handled it, and why. Think of it as a logbook that tracks evidence from seizure to courtroom. We can also take pictures where we photograph devices, serial numbers, connections, and even the scene where the evidence was found. These photos serve as visual proof of the evidence's condition and our professional handling. We can also block EMF signals or electromagnetic frequency signals by putting devices in special bags called Faraday enclosures. These bags essentially block electromagnetic signals, preventing someone from remotely wiping a phone or sending commands to delete evidence. In Kenya, for instance, we've seen cases where criminals used mobile networks to remotely erase evidence from seized phones. We can also minimize activity on seized devices. That means we don't turn on seized devices or open files unnecessarily. Every interaction with a device can overwrite evidence, and this is very important to remember. We also maintain device state. So if a device is on, when we seize it, we keep it on. If it's off, we keep it off. This preserves volatile memory that might contain crucial evidence. Physical security is also another one, where we store evidence in secure facilities with restricted access and we document every transfer. Evidence stored improperly can be challenged in court. And just to go a little bit deeper into some of these, chain of custody is like a detailed diary for evidence. Every time evidence changes hands, we must document who gave it, who received it, when the transfer happened, and why it was transferred. We record evidence descriptions, custodian names and signatures, and exact dates and times. This documentation proves that evidence hasn't been tampered with between seizure and court presentation. In Kenyan courts, a broken chain of custody can result in evidence being thrown out, regardless of how damaging it might be to the defendant. Photography serves as visual documentation of evidence condition and our professional handling. We photograph devices showing serial numbers, model numbers, physical condition, and any unique characteristics. We also photograph the scene where evidence was found, including cable connections and the device's position. These pictures help us recreate the scene later and prove we handled evidence properly. In court, a picture can be worth 1,000 words in explaining to a judge or jury what we found and how we handled it. EMF, or electromagnetic frequency signal blocking, is crucial in our mobile connected world. We immediately place seized devices in Faraday bags or enclosures that block all radio signals. Think about cellular, Wi-Fi, Bluetooth, and even GPS signals. This prevents remote wiping, where criminals send commands to delete evidence from seized devices. It also prevents new data from being received, which could overwrite existing evidence. We've seen cases, for instance, where criminals used Find My Phone features to remotely wipe devices, or where continued message reception overrode deleted WhatsApp conversations we were trying to recover. Faraday bags are like putting the device in a radio-proof box. Nothing gets in or out electronically. Even with good intentions, interacting with seized devices can destroy evidence. Every time we open a file, the computer updates its access time. Every time we run a program, we might overwrite temporary files or memory areas. If we log into accounts, we might trigger automatic deletion of old data or overwrite browser history. The golden rule is, don't touch anything unnecessarily. If devices are password protected, we use forensic techniques to bypass security rather than asking suspects for passwords, which they might refuse to provide or could give us fake passwords that trigger data deletion. This rule is about preserving volatile evidence. That means information that exists only while a device is powered on. If a computer is running when we seize it, the RAM contains information about running programs, passwords that were entered, and network connections. If we shut it down, this information is lost forever. Conversely, if a device is off, we don't boot it up because the startup process would overwrite evidence and change file timestamps. The only exception is extreme circumstances where we can see evidence being actively destroyed, and shutting down is the only way to stop it. Physical security means controlling who can access evidence and where it's stored. Original evidence should be stored in secure facilities like forensic laboratories or evidence safes. Only authorized personnel should have access, and every access should be documented. We never leave evidence in cars, offices, or other unsecured locations. In Kenya, proper evidence storage facilities are still being developed, but the principle remains the same. Evidence must be secure and access must be controlled and documented. Now that we've preserved evidence, we need to acquire it properly, meaning make forensic images that we can analyze. Forensic acquisition is the process of making exact copies of digital storage media while preserving evidence in its most original form. Think of it as creating a perfect digital photocopy of a hard drive, including all the deleted files and hidden data. The goal is to create a working copy that we can analyze without ever touching the original evidence. This process must be done using specialized tools and techniques that don't alter the original evidence in any way. The forensic image we create should be identical to the original, bit for bit, and we use mathematical techniques called hashing to prove this. When acquiring digital evidence, we need to make several important decisions. First, do we use static forensics or live forensics? Static means the device is powered off, which gives us the most accurate and repeatable results. Live forensics means acquiring data from a running device, which lets us capture volatile memory, but it's less repeatable. Second, the order of volatility. We need to capture the most volatile data fast because it disappears quickly. RAM, for example, might disappear in seconds, while hard drive data might persist for years. Third, forensic tool selection. We only use proven, industry-accepted tools that don't alter evidence. Tools like NCASE, FTK Imager, and Autopsy are examples of forensically sound software. The important note here is that static acquisition should be preferred unless volatile data is critical to the case. Static acquisition is more reliable and gives us repeatable results, which is crucial for court proceedings. Static acquisition is our gold standard because it's repeatable and non-intrusive. We power off the device and create a bit-for-bit copy of the storage media. This approach is perfect for cases involving identity theft, electronic fraud, or unauthorized access where we need to prove exactly what files existed and when they were created or modified. Live acquisition is used when we need to capture volatile data like RAM, running processes, or network connections. This might be crucial in cases involving malware, active hacking, or when we need to see what programs were running at the time of seizure. For example, if you're investigating a case where someone is suspected of hacking into a government system, we might need live acquisition to capture the hacking tools in memory and active network connections. But for a case involving fraudulent documents or financial records, static acquisition would be more appropriate and reliable. Physical acquisition creates a complete bit-for-bit copy of the entire storage device, including deleted files and unallocated space. This is the most thorough approach and allows us to recover deleted evidence. However, it takes longer and requires more storage space. Logical acquisition only copies the files and folders that are currently visible to the operating system. It's faster and requires less storage, but we might miss deleted files or hidden evidence. Physical acquisition is generally preferred for serious investigations, while logical acquisition might be used for time-sensitive cases or when storage space is limited. Think of it this way. Physical acquisition is like photocopying every page of a book, including the blank pages and notes written in margins. Logical acquisition is like copying the pages with visible text. We have three main options for storing forensic images. Raw format, like Linux DD, creates uncompressed bit-for-bit copies. It's fast and compatible with most tools, but requires storage space equal to the original evidence. Proprietary formats like NCASE E01 can compress images and split them into smaller segments, making them easier to store and transfer. They also include metadata like case information and hash values. However, they are often only compatible with specific tools. Advanced forensic format tries to combine the best of both worlds. It's an open standard that supports compression, metadata, and cross-platform compatibility. The choice depends on your tools, storage capacity, and case requirements. When dealing with live systems, we must capture the most volatile data fast because it disappears quickly. This slide shows the timeline from nanoseconds to years. Memory and cache data might disappear in nanoseconds when power is lost. Running processes and network connections might change in milliseconds, and system configuration persists for seconds to minutes after shutdown. Storage media like hard drives and USB drives can preserve data for years, while backup media like CDs can last decades. The key point is that we must work systematically from most volatile to least volatile, and we must document what we captured and what we lost. In a practical investigation, this might mean capturing RAM first, then running processes, then network connection, and finally creating images of storage devices. We must also document any volatile data that we lost during the process. Different tools have different capabilities, and we must choose the right tool for each task. This table shows that tools like FTK Imager and EnCase are excellent for computer acquisition and general forensic analysis, while specialized tools like Celebrite are needed for mobile device acquisition. The key requirements are that tools must be forensically sound, meaning they don't alter evidence, and they must be appropriate for the type of evidence we are dealing with. We also need tools that can produce court-admissible reports and work with standard forensic image formats. Tool selection might be influenced by budget constraints, training availability, and the types of cases we typically handle. The most important thing is that whatever tools we use, they must be proven, documented, and forensically sound. Now we move to the analysis phase, where we examine the forensic images to find evidence and reconstruct what happened. The analysis phase is where we become digital detectives, searching through forensic images to answer the 5 W's and 1 H questions. The critical rule is that we always work with verified copies, never the original evidence. We can start by browsing directories and folders, looking at both visible files and unallocated space where deleted files might be hiding. We then index and search using keywords relevant to our case. For example, if we are investigating financial fraud, we might search for bank names, account numbers, or terms like transfer and payment. Parsing, extracting, and carving involves recovering data from compressed files, reconstructing fragmented files, and examining files in detail. Data carving is like digital archaeology. We piece together file fragments to recover complete files. Decryption can be challenging but necessary when suspects use encryption to hide evidence. We might use password cracking techniques or look for encryption keys stored elsewhere in the device. File header analysis helps us identify files whose extensions have been changed to hide their true nature. A criminal might rename a document, for example, from .doc, which is a Word document, to .jpg, which is a photo, to hide it, but the file header will reveal its true type. Finally, we can bookmark and correlate evidence, tagging important findings and looking for connections between different pieces of evidence to build a complete picture of what happened. Criminals use various techniques to hide or destroy evidence, and we must be prepared to combat these anti-forensic methods. Encryption makes data unreadable, but we might find encryption keys or passwords stored elsewhere, or use specialized cracking techniques. Steganography hides data within other files. For example, secret documents might be hidden inside innocent-looking photos. We use specialized tools to detect and extract hidden data. Signature masking involves changing file extensions or headers to hide data. Criminals might rename sensitive documents to look like system files, for example, or change image files to look like text files. Data saturation means flooding devices with irrelevant data to make our analysis more difficult and time-consuming. We combat this with automated analysis tools and careful case management. Malicious timestamps involve changing file creation, modification, or access times to mislead investigators about when events occurred. We look for timestamp inconsistencies and use multiple sources to verify timing. Broken log files with special characters or corrupted data can make analysis difficult. We use specialized tools and techniques to repair and analyze damaged log files. Have you ever wondered, is data permanently erased when deleted? This is a crucial concept that many people don't understand. When you delete a file and empty the recycle bin, the data isn't actually erased from the hard drive. Instead, the computer just marks that space as available for new data. The original data remains until it's overwritten by new files. This is why digital forensics can often recover deleted evidence even months or years after it was deleted. However, the longer we wait, the more likely it is that the deleted data will be overwritten by new data, which is why quick response is crucial in digital investigations. The final phase is reporting our findings in a way that non-technical people can understand and use. After all the technical work, we must communicate our findings clearly to people who may not have technical backgrounds. This can include lawyers, judges, corporate executives, or even police officers. Our reports must be comprehensive yet understandable. Procedures and methodology documentation must explain exactly what we did, how we did it, and why we did it that way. We include hash verification results to prove our forensic images are identical to the original evidence, and complete chain of custody documentation to prove evidence wasn't tampered with. We must identify all forensic tools used and explain why they are forensically sound. The credibility of our findings depends on using proven, accepted tools. Screenshot demonstrations help non-technical readers understand our findings. Instead of just describing what we found, we show pictures of the evidence with explanations. Findings and conclusions must be factual and based solely on evidence. We describe what we found, what it means, and what conclusions we can draw. We must be careful to separate facts from opinions and clearly identify when we're providing professional interpretation. Recommendations might include security improvements, policy changes, or additional investigation steps based on our findings. Expert testimony is often required, where we present our findings in court and answer questions from lawyers and judges. This requires strong communication skills and the ability to explain complex technical concepts in simple terms. In Kenya's legal system, for instance, digital evidence is becoming increasingly important, but judges and lawyers are still learning how to handle it properly. Our role is to bridge the gap between technical evidence and legal requirements. That concludes our introduction to digital forensics. We've covered the 5-phase investigation lifecycle, from identifying and preserving evidence through acquisition, analysis, and reporting. We've explored the challenges of anti-forensics and the importance of proper procedures for legal admissibility. Remember, digital forensics is both a science and an art. The science involves following proven procedures and using validated tools. The art involves knowing where to look for evidence, how to interpret what we find, and how to present our findings effectively. As we continue to digitize and cybercrime evolves, the need for skilled digital forensics professionals will only grow. Whether you're in law enforcement, corporate security, or considering a career change, these foundational concepts will serve you well. If you have any questions about what we've covered, you can reach out to me via the Hackett team, and I'll be happy to elaborate on any aspect of digital forensics or discuss specific scenarios you might encounter in your work. Thank you.